Good evening, everyone. Yes. Okay. So let's start today's session. Yes. So first of all, good evening, everyone. Yeah. So good evening, everyone. Welcome all of you for today's 11th live interaction session on MATLAB based programming lab in chemical engineering. So myself, Prasil Kapadia. Uh, I completed my BTech from SVNIT Surat in 2019. After that, I worked in Reliance Industries Limited at Jamnagar for a year. There I learned how to use S-Pen software with real world problems. Then I completed my master's from IIT Kharagpur in 2022, where I learned a similar course on MATLAB by Professor Parag Deshpande. Currently, I'm pursuing my PhD from IIT Bombay. This is my webpage and LinkedIn where you can connect with me, and this is the link of YouTube channel where all the videos of these live interaction sessions are getting uploaded. So let's start. Okay, we will solve this problem later on. First, let's start with previous year's assignment problems. Uh, just a minute. Okay, so let's start with the first problem. The first problem states that the PDE toolbox in MATLAB uses dash for solution of several type of PDEs. So we are having various options. So let's first know what are these methods. So what happens in finite difference method? In finite difference method, we divide our domain into grid points. Grid points. Okay, so let's say this is our domain. So what do we do in finite difference method? We divide this one point to one point, this to this point, this to this point. So this is called finite difference method. Okay, what is finite element method? So in finite element method, we divide our domain into various elements. What kind of various elements? Like we can divide it into triangle, like that. Let's say this is my domain, so I am dividing it into triangle like this. So this is called finite element method. In finite volume method, name itself suggests that we divide our domain into volume, elements of particular volume. Okay, some particular values of volume we divide our this domain. And in method of lines, what actually happen, we use we first divide our domain into points. Then what do we do? On spatial coordinates, on spatial coordinates, what do we do? We convert PD into these points. And then at each of that points, we are having time derivatives. So these time derivatives, those are solved by using, let's say RK2 or some inbuilt MATLAB codes. Okay, so these are various methods available. So let's first see what is there in PDE toolbox. So I'm keeping this for now. So let me go to MATLAB first. So in your MATLAB, if PDE toolbox is not already installed, you will have to install it from help desk. So let's open the MATLAB. Okay. So to find that, I need to go to apps, and in apps, it is here PDE modeler. If it is not available here, then you need to wait. I will show you. Let it just open it. Okay, so if it is not available, so what do you need to do? You need to write PDE modeler in search window. Sorry, not here. In apps here, you need to check it. No. Yeah, here you need to go to install, not install app. You need to go to this. Yeah, here you need to go to get more apps option. So there you need to search for this PDE modeler. If it's not available, then you have to install it. Let's see if I am writing PDE modeler. So see, this is coming PD tools box and it is already installed. So this option is not there. Let's say if something is not installed in my MATLAB directory, let it, yeah. Let's say this Simulink is not installed in my system. I have not installed it. It's not required for me. So what happens if I want to install it? So here there is the option of install, but PDE toolbox is already there installed in my system. So this install button is not there. But if it is not there in your system, you can install like this. Okay. So see, if you read about this description, that partial differential equation toolbox provides functions for solving structural mechanics, heat transfer, and general partial differential equations using finite element analysis. So here what we can do, we can perform linear static analysis to compute deformation, stress, and strain. These are additional applications for modeling structural dynamics and vibration. The toolbox provides a direct time integration solver. You can analyze a component's structural characteristics by performing model analysis to find natural frequencies and mode shapes. You can use model function dominant heat transfer problems. Those we are going to solve. You can also solve standard problems such as diffusion, electrostatic and magnetostatics, as well as custom PDs. Partial differential equation toolbox lets you import 2D and 3D geometries, and you can automatically generate masses with triangular and tetrahedral elements. These elements we can use. Okay, so uh, let me, yeah, these I don't need right now, so I'm closing this. This is also okay. Let's keep this. Okay, so let's say I'm creating some kind of uh, wait. Okay, it is not responding. Yeah, so let's say I'm having some kind of geometry. I'm preparing a geometry of square. So what I need to do, I need to first go to draw and click on draw mode. Then I need to select something and let's see if I'm drawing it. It's not working. My screen is not. I guess there is the issue with my screen. Yeah, see, now it happened. So what you can do, I have drawn the element. Now what I have to do, I have to create the mesh. So if I go to mesh mode, so see, these are triangular meshes available. You can also refine them, or you can also jiggle them. There are various options available. Okay, so this is how you can um, create your element. Okay, so back to our question. So the question was PDE toolbox in MATLAB uses dash for solution of several types of PDE. So our correct answer is option D, finite element method. Okay. So moving ahead with the next question. In the draw mode of PDE toolbox, combination of a solid object is done by formula of set algebra plus minus or multiplication. So this is correct. If you want to combine some, these I will not show you, but if you want to combine some objects, then you can use this kind of algebraic notations to do that. Okay. Okay, now next question. For what values of x and y will the following PDE be elliptic? Okay, so what is the criteria of PDE to be an elliptic PDE? Okay, so the elliptic PDE is when b square minus AC is less than 0. Okay, This is the criteria. And my equation is A del square U by del X square plus 2 into B del square U by del X into del Y plus C del square C into del square U by del Y square is equal to 0. So if we compare it with this equation, so what is the value of A? Value of A is equal to 1 plus Y. Correct? What is the value of B? My value of B, my 2B is equal to minus 2, 1 minus X. So my value of B is equal to minus of 1 minus X. So X minus 1. And my value of C is equal to minus of 1 minus Y. That is nothing but Y minus 1. Okay. So if I do this B square minus AC. So B square is X minus 1 whole square minus AC Y plus 1 Y minus 1 should be less than 0. So x minus 1 whole square, I am not elaborating it. And y minus y plus 1, y minus 1 is nothing but y square minus 1. So y square minus minus plus 1 is less than 0. Okay, so this will be my criteria for this equation. Okay, let's look out from the option. If I put x is equal to 0, and y is equal to 1. So x is equal to 0 and y is equal to 1. What will be the value? X is equal to 0. 0 minus 1 whole square is 1. Y is equal to 1. Minus 1 plus 1, that is 1, and that is greater than 0. Okay, so this is not a criteria. So this is not the option. Okay, if I keep x is equal to 1, y is equal to 0. So x is equal to 1. 1 minus 1, 0. 0 whole square is 0. Minus 1 plus 1, that is equal to 0. So this is also not the criteria. If I put x is equal to 2, y is equal to 1. Let's see, x is equal to 2. 2 minus 1 whole square is 1 minus 1 plus 1 is equal to 1. That is again greater than 0. So this is also not the correct option. If I keep x is equal to 1, y is equal to 2. So 1 minus 1 is 0. 0 square is 0 minus y is equal to 2 plus 1 is minus 1, that is less than 0. So this is our correct answer. So for this elliptic to be for this PDE to be elliptic PDE, my x should be equal to 1 and my y should be equal to 2. Okay. For hyperbolic PDE, what is the condition? For hyperbolic kind of partial differential equation, my b square minus AC should be greater than 0. And for parabolic, my b square minus AC should be equal to 0. Okay. So if we see these options, so for option 1, it is greater than 0. So option 1 is nothing but hyperbolic PDE. Then option 2, x is equal to 1, y is equal to 0, it is equal to 0. So it is nothing but parabolic PDE. Correct? And my x is equal to 2, y is equal to 1, it is again positive. So it is again hyperbolic PDE. And for this option, it is elliptic. So various kind of question. Here also you can prepare various solution. Let's say if I'm putting x is equal to 1. No, let's say if I'm putting x is equal to 1 and y is equal to 2. I am putting it. So for that, sorry. So for that also, if I put 1, so 1 minus 1 is 0, minus 4 plus 1, minus 3 less than 0. So this is also one solution for elliptic partial differential equation. So our correct option is option D, x is equal to 1, y is equal to 2. Okay, so these kind of questions maybe will be there in your final examination. So just remember these rules or criteria. Okay, next question. Case hardening is a process by which the surface of a metal is hardened by a high temperature heat treatment during which carbon from the surrounding atmosphere diffuses into the metal. So what is happening in hardening, case hardening process? The surface of a metal, we need to hard the surface of a metal by high temperature heat transfer process. So what happens in this process? Carbon from the surrounding atmosphere diffuses into the metal surface. The increase in the carbon content raises the surface hardness, correct? The diffusion process is expressed by this law, Fick's first law, that is del C del T is equal to K del square C del X square. Here C is the concentration, D is the diffusivity, X is the space coordinate, and T is the time coordinate. When the initial conditions and boundary conditions of Dirichlet type, what is Dirichlet type boundary condition? Let's say X is equal to 0, my C is equal to Cx. X is equal to 1, my C is equal to Cy. These kind of conditions are called Dirichlet boundary conditions. It is necessary to use PDE toolbox to obtain the solution of PDE. Okay, let's go to MATLAB help section. So we have two options, correct? So, okay, first let's see here. Okay, now let's go to this help section only. So for this PDE modeler, what kind of equation we can solve? If it is written here, it is not written here. Wait, let me first search PDEP, that is MATLAB inbuilt function. If I search PDEP, so PDEP can be used to solve parabolic and elliptic PDEs. Okay, so let me write down here. We have one option of solving this using PDEP. So PDEP can be used to solve elliptic and parabolic kind of partial differential equation from here. Parabolic and elliptic PDEs, where PDE toolbox so it is governing in this. We can solve parabolic kind of equation, but that is not just the limitation. If I go to options, there is some option of no, not here. Yeah, here. PDE mode. If I go to PDE mode, no. Yeah, so here also we can solve elliptic, parabolic, and hyperbolic. Okay, but here what is told to us that it is necessary to use PDE toolbox. Correct? Their word is it is necessary to use. So this is not correct because it is not necessary to use this because we can also go for the option of PDE, PE, MATLAB inbuilt toolbox. So the correct answer is answer no. It is not necessary to use PDE toolbox. We can also use PDE, PE, MATLAB inbuilt function. Okay. Okay. Question number 5, we will be solving it soon. Now let's move ahead with question number 6. So question number 6 is that a boundary value problem is a set of differential equation with a solution which also satisfies some additional constraints known as what? So let's say I am having this equation d square t by dx square plus h into t minus t infinity is equal to 0. So for this kind of problem at x is equal to 0, let's say my t is equal to ta and at x is equal to L, my t is equal to TB. So these are, what is this called? Constraints. These constraints are called boundary conditions. So for boundary value problem, what is that? It is the set of differential equation with a solution which also satisfies some additional constraint known as boundary conditions. Okay. So the correct answer will be option A, boundary conditions. Okay. Question number 7. Considering a block with finite dimensions, in general, which among the following equations is correct for change in energy of block? So if we write heat balance equation, so what is heat balance equation? Let's say this is my element. So I'm just writing in one direction. So my heat in, let's say it is Qx, heat out, that is let's say Qx plus dx. Okay. So my uh, sorry. So let's say if I want to write is dq by dt, that will be equal to heat in minus heat out. Plus there is one additional term of, let's say there is some element placed in it that is generating heat with some, let's say uh, this m. Heat generation term is plus m. Okay. So what is the equation, which equation is correct for change in energy of block during time span c? So we are asked dq by dt. So what is that? Heat generated in element during time dt. Okay, let's first this term heat flow into the element during time dt minus heat flow out of element time during time dt. So it should be heat flow in minus heat flow out plus heat generated. So if we see these options, so this is the correct option where heat generated in the element during time dt, this term is there first, plus heat flow into the element during time dt minus heat flow out of the element during time dt. So qx minus qx plus delta x plus some generation term m. So option B is correct. Okay. Let's move ahead with the next problem. When does the general heat conduction equation, which gives the temperature distribution in an isotropic solid, reduced to Laplace equation? What is isotropic solid? Isotropic means directions. Um, their properties of are independent of direction. That doesn't depend on direction. Let's say if it's thermal conductivity. Okay, let's search it. I just want to be confirmed. So what is isotropic solid? Isotropic solid, same physical properties in all direction. Okay, so the same thing that I told you, properties does not depend on direction. So what kind of properties? Let's say my thermal conductivity k, let's say it is in x direction it is kx, in y direction it is ky, and z direction it is kz. If it is that if it is that kind of condition, then it is called an isotropic solid. But here it is told that isotropic solid. So what is our heat equation? Our heat equation is del square T by del x square plus del square T by del y square plus del square T by del z square plus Q by K is equal to okay, let me del T by del T, but I guess there is some multiplication involved. Let me just check it. I guess there is some multiplication. I'm not sure. So I just want to confirm that. Yeah, so this kind of equation 1 upon alpha del T by del T. Yeah, that is the term. What is that? Alpha is thermal diffusivity. That is equal to 1 upon alpha del T by del T. Okay, this is my heat equation. Correct. Now, what is my Laplace equation? So my Laplace equation is del square T by del x square plus del square T by del y square plus del square t by del z square is equal to 0. This is my Laplace equation. So what is asked, when does the general heat conduction equation, which gives the temperature distribution in an isotropic solid, reduces to Laplace equation? So when does it this, when this heat generation term q is equal to 0 and my del T by del T is equal to 0. Okay. So option A is body is unsteady state. If it is unsteady state, this won't be 0. So this is not correct answer. Body is in steady state with heat generation. If body is in steady state, this term is 0, but this term is there. So it is not an Laplace equation. Body in unsteady state, it is not possible. So correct answer is this only. Body is in steady state with no heat generation term. Correct. So remember this equation. This is heat equation, and we can convert it into Laplace equation when there is no heat generation term and when there is steady state. Okay, let's move ahead with the next problem. The PDE toolbox of MATLAB is well suited to address the problems in the domains of structural mechanics, electromagnetics, heat transfer, or all of the above. The answer is all of the above. This we already looked at in the description part of PDE toolbox. So here also, if we go, there are various kinds of options available. Where did that go? No, not in examples. Sorry. Wait, let just this go away. Yeah. अरे यार, wait. PD mode, no. Maths. There are various options available. Yeah, here. You can, no, these are for system, but see here, this is heat transfer equation, electrostatics, magnetostatics, structural mechanics, with plane stress and plane strain, then conductive media, DC, this and diffusion also we can study. So the correct answer is here option D, that is structural mechanics, electromagnetics, heat transfer, and all of the above. So the answer is all are correct. So all of the above. Okay, next move ahead with the next problem. Which of the following is a condition for the second order partial differential equation to be hyperbolic? Correct. So this we remember, this less than 0 is for elliptic. Correct. This equal to 0 is for parabolic. This greater than 0 is for hyperbolic, and is less than equal to 0, there is no conditions available, and this is subject to my equation is A del square u by del x square plus 2 into B del 2u del x with respect to del y plus C del 2u by del y square. This is the equation given to us. So when this kind of equation is there, then my b square minus AC should be greater than 0 for hyperbolic. Correct? So my option is option C, b square minus AC greater than 0 for this hyperbolic condition. Okay. Okay. So this is all about PDE toolbox. Let's try to apply this PDE toolbox with one example. Just give me a minute. Okay. So let's move ahead with the next our problem statement for solving PDE toolbox. Okay. So okay, I'm closing this everything as of now. So what are the steps? Okay. To first create a geometry, draw a rectangle. Okay, I just want the steps. This is also another way to open PDE modeler by using this command. Okay, so I'm just closing it as of now. I'm closing this. I don't need to save it. Now I will again open it by using this PDE modeler command. Okay, so see, screen is available. Okay, so let's first see what is the problem statement saying to us. A metal plate of 1 meter cross 1 meter is placed such that its four edges are kept at different temperatures shown in the figure. Okay, so this is the metal plate of 1 meter length by 1 meter length. So all are 1 meter length. Now what is told to us at x is equal to 0, y is equal to 0, x is equal to 1, y is equal to 0. These are four boundaries. Now at this edge, my temperature is 20. At this edge, my dt dy is equal to 0. Then at this edge, my temperature is 40. And at this edge, my temperature is 30. The steady state temperature distribution in the plate is given by the Laplace equation. So what does this mean? We are not having any unsteady state term plus there is no heat generation term. So that equation is del 2t del x square plus del 2t del y square is equal to 0. Find the correct temperature distribution in the plate. Okay. So let's first try to draw the element. Okay. So I will draw the element of 1 cross 1. So what do I need to do? I need to first go to draw. I need to click on draw mode. Okay. Then see where there are various shapes available. This is rectangle. Click and drag at corner to create rectangle. This is also for rectangle, but I guess this is for this more centered rectangle or centered square. Okay. So I am just doing it. So what is my length? My length is from 1 to 1 cross 1. I don't know why it's not forming. I just have to click it. Okay, I am here on. Okay, I guess from here I can do it. Yeah, so see, I just created it, right? But what is the issue? I'm told that it is 1 cross 1. So in x direction, it should be 0 to 1, and in y direction, it should be 0 to 1. But that is not our case. So how can I modify my dimensions? So one thing is to create this like 1 cross 1, if you can do it. Or what is another option? Just double click on the element. Okay. So what is told on left? What is my left coordinate is 0. These are 1 1. Okay, so see 0 to 1, 0 to 1. So what did I do? In my left and bottom. So this left and bottom it is 0 0, and my width is 2 and my height is 2. Okay. So let's say this is we can give it some name. What is the problem? Okay, this is problem 1. Let me just do control less. This is my problem. Okay. So what can I do? Now, okay, one more thing. You can see that this space is not required. So can I format my axis? Let's search that if we can do it. So if we go to edit, no options, yeah, axis limits. Okay, so we can give x-axis from minus 0.5 to 1.5 and y-axis also minus 0.5 to 1.5. Okay, so see, this is a better representation compared to the previous one. And here we can give some name. So let's say heat transfer, transfer. What is the problem statement? Heat transfer Um, okay, I'm just writing it problem one. One. Okay. So this is the name. Okay. Now, what are the additional details told to us? Okay, so at each boundaries, various conditions are given to us. So what we can do? Okay, so before that, what do I need to do? I need to create the mass. Okay, so I will go to initialize mass. Sorry, I will go to this refine mass. No, I will just go to mass mode option. So when I click on mass mode option, then I need to click on refine. Yeah, I clicked on mass mode option. So now there are various masses available. So this is this kind of mass. Okay, I'm just doing this. Just a minute. Okay, we did this actually, but we are in mass mode, and let's say I want this kind of mass, but why it's not working? Sorry, students, just give me a minute. Let me check if I'm doing something wrong. Now, first we need to do this only. We are not in true mode. No, we didn't don't want grid. No, these also don't. We don't. Okay, just a minute. Okay, let's first go to, yeah. Okay, I found the problem. So first, what do we need to do? We need to choose our problem. So what kind of problem this is a heat transfer problem. So I will just choose heat transfer option and I will go to mass mode. I don't know why it's not coming out. Yeah, this I am creating by my own, but this is something that I don't want. Okay, let's first add our boundary conditions. So for that, I need to go to option of heat transfer. Okay. So it will give boundaries according to heat transfer. So first, I will click my boundary mode. So what is my first boundary condition? At this edge, my temperature is 20. At this edge, if I click here, so I am in boundary mode. I don't know if my laptop is slow or what is the issue. Okay, yeah, this is not required. Yeah, now it's in boundary mode. Yeah, now it is in boundary mode. Yeah. So when I click it, it is coming out as a okay. Yeah. Okay. So for that, what do I need to do? First, I need to enable my boundary mode. I have enabled it. Now I need to click on specify boundary conditions. Yeah, this is only giving me length only. Control V. Okay, let me just click it here. No, student, just give me a minute. I guess I am doing something wrong. Be like this only. It should be like this only, but I don't know why it's not working. I just have to. Okay, let's do one thing. I'm closing everything. I'm redoing it because I guess there is something selected and I'm not able to redo that, undo that thing. So let's do it from zero. I will just close everything. I will go to apps and I will go to this PDE modeler. It's really easy, but currently it's not working. Okay, so see, this we have opened. Now I need to go to draw. I need to click on draw mode. Correct? Now let's say I'm drawing something. Yeah, first I need to select heat transfer. Okay, this is step one. Okay, I am in draw mode. Okay, so I have to draw something. Let's say I want to draw a square. Okay, I have drawn it, but I need to change the coordinates. So I will just click it here. I will click here 0. Then here also 0. Then 1 and 1. Okay, this is what we have done as of now. And we can also edit our axis from axis limits. So let's say it is minus 0.5 to 1.5. Here also minus 0.5 to 1.5. Or okay, let's do one thing. Let's just keep 0 to 1 and 0 to 1. Okay, so it is closed. Okay, now I need to go to boundary mode. Okay, so boundary mode is enabled. Oh yeah, now it worked. See, so boundary mode, our boundary condition is of Dirichlet type condition. So what was the condition? At this edge, my temperature is 20. So what do I need to choose? I need to choose Dirichlet, and this R is my temperature and my temperature is 20. Let's not worry with weight part. So I am pressing OK. Now for this boundary, what is that? Here it is del T del Y is equal to 0. So what is that del T del Y is equal to 0? That is Newman boundary condition, correct? So my del T del Y is equal to 0. So that is represented by this term. Yeah, del T del Y is equal to 0. So both are anyway 0. We are not worrying about Q is not anyway there. G is also 0. And this is okay anyway 0. Okay. So this is anyway correct. We don't need to do anything here. Okay. Then this boundary. It is Dirichlet boundary condition with temperature is equal to 40. Okay. So here I will press my temperature is 40. Okay. And here, what is the temperature? Let's say my temperature is here 30. So I'm just pressing it 30 and keeping it okay. Okay. Now what do I need to do? I need to go to mass mode. Okay. So see, messes are there. Okay, I guess it was the issue with something with that PD modeler because it was not working. Currently, we are not doing anything different. It is same. I just want to change this limit to for better representation. I to 1 point. Okay. Yeah. So see, I have also created mesh. So what I can further do? I can further my refine the mesh. Okay, the more refined it is, the more accurate we will get the solutions. Okay, so this is really refined. So see, at almost every point it is going to calculate. So what do I need now? I just need to solve the PD. So it is, I guess it will take some longer amount of time because we have refined it. So see, what is it showing? So this 40 is here. This temperature is near to 40. Are we getting that? Yes, this is 40. Then this point del T del Y is 0. So that is something we are not getting. Del T del Y is equal to 0. Here we are getting 20 and here also we are getting 30. What is del T del Y 0? This should not change. But it's not going to happen, right? Let me just check previous year's assignment. So what kind of plot they are getting? Yeah, they are also getting similar to us. Okay, so our option is, so the procedure that we have followed is correct. Okay, so this is how we can solve it. I will again show it to you by saving this thing. So control save as. Okay, let me close it so it will. Yeah. So which assignment this is? This is assignment 10. Problem 1. Okay, so it is saved. So I will again show you how to solve it. So it is more clear. So for this, any kind of this kind of problems, what do I need to do? I need to open this PDE modeler. Then I need to first go to draw mode. I have enabled draw mode. Then I need to select this option. So see, I have created a shape, but shape is not correct. So what can I do? I can change this X and Y value. So it is uh, it's 1 1. Height and width both are 1. Okay. So X is equal to 0 to 1, 0 to 1, 1 to 0 to 1 and 0. Yeah. So we can also edit our axis limits. Let's say here it is from, okay, let's do similar to this. It's not required. 0.5 to 1.5 and here also let's say 0.5 to 1.5. Okay. Yeah, here it should be negative. Correct. Now I will close it. Then what do I have to do? I need to define, go to boundary mode. And then I need to click on this. So what is the temperature here? The temperature I guess here was 20. Okay. Then similar thing. What is the temperature here? Here its temperature is not given. Here Newman boundary condition is given. That is this Q term is also 0 and this G is also 0 because our term is del T del Y is equal to 0. Okay. So this is also correct. Then this term. What is the temperature here? Here it is 40. Sorry. This term I need to change, that is 40. And here, I guess it is 30. Yeah, it is 30. 30. I have pressed OK. Then will go to mass. I can click on mass mode. And now I can, what can I do? I can reinitialize my mass. Sorry, I can refine mass. And I can just solve my PD. Okay, so it will show me temperature distribution. Okay. I just want to confirm a thing. Yeah. Okay. So we have solved this problem. So how we can play further? So what I can do, I can change my boundary conditions. Let's say this value. Yeah. Let's say my this boundary condition. My temperature is 40. Here is also 40. And here is also 40. And both these ends, my this del t del y term is 0. But let's say I am having some heat generation term of some 20. And if we wait, and if we solve this, yeah, it automatically took mass. So see here, here it is 40, here it is 40, here it is del t del y 0, and here there is a heat generation term. Okay, so this is how you can play with boundary conditions. If I again go to boundary mode, okay, so this is, let's keep this 0 here. Let's say this is my, sorry, I'm clicking this. So what was this condition? It was 20. So let's say this is 20. Then this is 0. Let's say this is 100. This Dirichlet is 100. And this is 40. So temperature distribution will be changed. I need to solve it. So I will get something different this time. Okay. So this is 100 here. Okay. So as we are having 4 boundaries, we can define 4 boundary conditions. Okay. I just want to do one more thing. I will go to boundary mode. Yeah. I will go to boundary mode. Let's say here I am having this G term. G term should be equal to, let's say it is 10. I'm just changing it and I'm solving my PDE. Okay. So when it is 10, then my solution is changed. Okay. So this is how you can play. If I go to plot, so I don't think it is going to show something. This is only our plot. PDE solution plotted. Colors are changed. Nothing else. We can play here at our own. So see here shadings are different. So see here it is some arrows are added. Okay, so what does this arrow mean? Heat is flowing from here to here. Correct. Let's say if I am changing my boundary conditions, I just want to see if arrows are changing or not. So let's say here it is 20. I will just for now keep both 0. And let's say this term is 10. Okay. So if I solve this PD, so see, my arrows are changed from here to here. So heat is flowing from 20 to 10, higher to lower temperature. So this is a good. You can also explore many things from here. Deform parameters. Okay. Let's plot. Let's keep everything. I just want to see how it looks. Okay. So this is 3D plot. Not 3D plot. It can't be 3D plot because it is XY. It's just representation with arrows. Okay, so we have learned how we can solve this kind of heat transfer problem using PDE modeler. Okay, so let's try to solve one more problem. I will close this window. I have already saved it, so I don't need to save this again. So what do I will do? I will again open PD modeler. So before that, let's have a look at problem statement. This problem is a bit different than the previous one. So here what is told to us, consider a long metallic bar. Thermal conductivity K is equal to 1.5 watt per meter Kelvin of a square cross section of side 0.1 meter as shown in figure 2. The four sides of the bar are subjected to the different boundary conditions. Okay. Solve the problem numerically using MATLAB PDE toolbox and plot the steady state temperature distribution in the bar that we have already done in previous problem that we will again do. What is the steady state temperature at the center of the bar? This is something we are supposed to find new. So what is that cross section of 0.1 meter? Okay, square. So we will go to apps, we will go to PDE modeler. Okay, it is opening. So what is the first step? The first step is to define the size, sorry, to define the shape. So for that, I will go to draw option. I will click on draw mode. Then I will go to again and choose rectangle. I am just plotting something, but what do I need? It is 0.1, 0.1. So I will keep 0, 0, 0.1. Okay, so see here it is looking really bad. So what I will do, I will go to options. I will go to X limits, axis limits. So it is 0.1, 0.1, correct? So I will go to minus 0.1 minus, no, I don't need to go to minus. I can go to 0 to 0.2 on both X and Y axis. Okay, our shape is not correct. Yeah, it is 0.1 cross 0.1. Okay. I'm sorry. Let's do one thing. And this is not looking good actually. I guess this will work. Yeah, this is somewhat better. Or we can choose 0.05 to 0.15. We should just focus on our main focus should be on object. Yeah, this is still better. If I'm keeping 0.01, it is going to be uh there will be very small amount of space. Yeah, okay, this is fine. So I have applied it and I will close it. Okay, now here, what is the difference? So here, okay, let's do it. Isothermal boundary condition T is equal to 100. This we can easily apply. So what do I need to do? I need to go to boundary mode. Then here, what is isothermal boundary condition? T is equal to 100. Okay, one important thing that we have missed. We first need to choose heat transfer mode. Okay, now we will go to boundary condition. So see, what is my temperature? 100. Okay, so I will put it. Okay. Okay. Then this side, my heat, constant heat flux boundary Q is equal to 10 raised to 3. Here it is H and T infinite are given and here insulated boundary is given. So what can we do here? So, some specifications I can directly give. So what is the value of thermal conductivity? Okay, is our PD elliptic? No, it is not elliptic. Yeah, it is this thing. Parabolic. So rho, what is the value of density? It is not given, so let's just skip it one. What is heat capacity? Heat capacity is also not given. Let's just skip it one. What is thermal conductivity is 1.5. Let's change the value of K is equal to 1.5. What is my heat flux? It is 10 is to 3 watt per meter square. What is my heat transfer coefficient? 45. And what is T external? That is 30. Infinite temperature. I'll just press OK. This boundary condition is already defined. Okay, this one is insulated. So both should be 0. I'll press OK. Here, uh, this T infinity and H are given. Here it's not given anything. So here also I will just choose. I can just keep it. No, temperature is not 0 here, right? Here there is some value of temperature. I can't write Newman boundary condition. Okay, let's do it. And this one, my Q is equal to 10 raised to 3. So I will go to Newman and I will write Q is equal to. Okay, let's try to solve this and see what we are getting. Okay, so this is my 100. That is correct. Insulation meaning no heat loss. Okay, so that we can't confirm. Then these two terms are there. Where on left boundary it is Q is equal to 10 raised to 3. Okay, let me just do one thing. I'm not keeping it. I'm keeping this term as 0. We'll just go to boundary mode. I guess it's not good to. I'm sorry. Uh, Now it is 1000. Let's keep it in this way. And this term, this is some problem I'm feeling it. If I keep it here, temperature is equal to 30. And because that can't be insulated. Now let me solve PD. It's not much changed. Yeah, okay, so this is what we are getting. So what we can play with here, we can play with this parameter. Let's say my thermal conductivity is very high. Let's say it is 50. And let's say I'm solving it now. I guess it is not changing anything significantly. This is coming uniformly 30. If let's say my thermal conductivity is really small value. Sorry. Mm, let's say it is really very small value 0.001. And I'm solving it. So thermal conductivity is not good. If it is really less, so meaning temperature won't change anyway because there is no heat transfer occurring. Okay. So this is how you can also play with parameters and see the effects. Fine. 45 and 30. Okay. So this is what it is. So I will just save this problem. Let's see, there are various things are coming up. Okay, I want to check one more thing. Just give me a minute, students. I have solved this problem in some different way, but I am not having that file with me. So there was some advanced heat transfer problem of some assignment. I guess it was test 2, not test 2, test 3. Yeah, it was this problem. It is taken, this problem is taken. So I'm just opening my solution. It's fun. So it, I have also created 0.1 comma 0.1 mass. Then see, I have written, okay, I have written everything. Q is also 1000 here. H is 1000. H is not 1000. 045, 00. Okay. I'm just concerned about this boundary, the condition that we mentioned here. Okay. Okay, so let's move ahead. So this is how we have learned how to use PDE toolbox. So let's just summarize this thing once again. I will open that PDE toolbox once again. So what do we need to do? Okay, so what do we need to do? We need to first define our draw the object. So I can go to click on draw mode. Then let's say whatever kind of thing, let's say I want to create an ellipse, then I can create an ellipse. Then here I can change those coordinates. Let's see if I am doing it. So let's say if I am choosing it a rectangle, some arbitrary rectangle, then what do I need to do? I need to go to, if I want to edit those axes, then I can edit those values of height and width. I can do it from here. Then if I want to have some axis limits, that I can also do it from here. Then what do I need to go? I need to click first on boundary mode. So it will enable boundary mode. Then I need to click on each boundary to write down the, okay, so first of all, first choose the kind of problem that you are dealing. Let's say if we are dealing here with heat transfer. So I need to click on the boundary and deter and give the values of whatever it is asked. This is how you can give the values by your convenience. Then you can go to wait. Then you can go to mass. So it will create a mass. You can also, so see, it is finite element because it is creating element, triangular elements. Okay. You can refine it. Then you can solve your PD. Okay. So this is how you can get your solutions. Okay. I don't want to save it. This is just a revision. Okay. Student, just give me a minute. I want to problem to. Sorry. Oh, this I can't open directly with this. I guess then there is no benefit of saving it. So I should have saved it. It's save as, not just save, because it is saving it in a code that is not required to us. Okay, so keep this thing in mind. Always click on save as, not on save. Okay. I guess this is not going to be useful. It's better if we directly save it. Just click on run. Will it show me that mode? I just want to try something. I don't know if it's going to work or not. It is directly opening here. So I need to run it. I just want to have some corrections here. Where is my PD? Sorry, this thing. I want to give this value of heat source as 10 to the power 3. And I need to click on boundary mode first. This is correct. So it's just consent here. If I click Dirichlet, it will go this. Here heat transfer coefficient is not low, but this term is 1000. Okay, this is the mistake that we did. Heat flux is 1000. I'll just control S and I will just close this thing. It will open it like this only. After that, you can. So this is all about PDE modeler. So till now, what we have completed till now, first we looked at solution of linear equations. Then we looked at solution of linear equations. Then we looked at what did we look? We looked at ODE, ordinary differential equation solution. For that, we looked at two kinds of problem. One was initial value problem, and second type was boundary value problem. Okay, so let's move ahead, and we will see on minimization or optimization of a function. Okay, just give me a minute. Something is, yeah. Yeah. Okay, so let's move ahead with minimization. So what is minimization? How do we minimize the function? Correct. So I will just open one blank slide. Let's say my function is x cube minus 3x square plus, sorry, I don't know why it's happening like this. My function is x cube minus 3x square plus 4x minus 0. So how do I find a minima? I first calculate this is my function. So what do? I first find a minima. So first I do del f by del x is equal to 0. That is x cube is 3x square minus 6x plus 3, that is equal to 0. And if I solve this, I get some values of x is one positive value, x is one negative value. Then what do I need to do? I need to find del 2f by del x square. That is 6x minus 6. If I put x is equal to a and x is equal to b, and if this del square f my del x square is greater than 0, then it is minima. My del square f by del x square is less than 0, then it is maxima. And my that second derivative is equal to 0, then it is called saddle point. Okay, so this is the simple thing. But when we are having multiple variables x and y, then also we can do it mathematically. But let's learn how to solve this using MATLAB. Okay, so for that we have some problem statements from previous year's assignment. So my first problem is use fminunc in MATLAB to determine the minimum function value of f of x is equal to e raised to x1 4x1 square plus 2x2 square plus 4x1 x2 plus 2x2 plus 1. Okay, so let's first search about this fminunc. What is that thing? fminunc. So for fminunc, find minimum of unconstrained multivariable function. What is unconstrained? That we are not giving any constraint. Let's say my x square while minimizing this particular function. If it is constrained, meaning that let's say I have a constraint that x square minus 2x plus 1 should be greater than 0. This constraint should also be fulfilled. Those kind of constraint, but it is unconstrained problem. So for that we can use this fminunc function. So what is the syntax? So x is equal to fminunc f function comma x0. Okay. So if this is the example, I want to minimize this x cube, this one 3x1 square plus 2x1 x2 plus x2 square minus 4x1 plus 5x2. I want to minimize this with initial guess of 1 comma 1. So let's write down this. This is not going to be difficult at all. So I will open a live script. I will write down as f is equal to at the rate of x. What is my equation here? 3x1 square, 3 into x of 1 square plus 2x1 x2 plus 2 into x of 1 into x of 2 plus x2 square, x2 square plus minus 4x1 plus 5x2 minus 4 into x of 1 plus 5 into x of 2. So this is my function. Okay. Now I want to find a minima. That what do I need? What is the syntax saying? I need x0. What is the syntax? It is function comma x0. So function I am already having. Now what is my x0? My x0 is, I can give some initial guess. Let's say my initial guess x0 is equal to 0 comma 0. Correct? And okay, there are various formats to write it. So if I just write it x, then it will give me the value of x. But if I also write f well, so it will also give me what is the value of my minimum function. So I will write in bracket x comma f well is equal to f mean unc. What is the syntax? X function comma f0. So I will write f comma x0 and I will run it. So my function value is minus 16.37 and my x are these two values 2.25 and minus 4.75. So my tolerance is 10 is to minus 6. Okay, so what is local minimum? So see, if this kind of curve is there, then this is called local minima. This is overall. So this is called global minimum. Okay. So further, what we can do? Okay. So this is how we can solve it. So let's take this problem and try to solve. Use fminunc in MATLAB to determine the minimum function value of this e raised to x1. Okay, this is a bit complex. So let's write it e raised to exponent of x1. Exponent of x1. Okay, let me clear this, else it is going to exponent of x of 1 into, be really careful when you are using brackets, into first term is 4x1 square into 4 into x of 1 square plus x2 square 2 into x of 2 square plus 4x1 x2 plus 4 into x of 1 into x of 2 plus 2x2 plus 1. Okay, this is the mistake. 4 into x of 1 into x of 2. Okay. 4x1 x2 plus 2x2 plus 1 plus 2 into x of 2 plus 1. Okay, this is my function. And what is told our initial guess is minus 1, 1. Minus 1, 1. Okay, if I run this, what is the value that I am getting? I am getting 0.5 and sorry, 0.5 and minus 1. So we are supposed to choose closest option. So 0.1 and minus 0.5 and minus 1. So closest is 0. So our correct answer is 0. If I go for instead of minus 1, 1, let's say I'm going with 0, 0. So then also I'm getting 0.5 and minus 1. But what is this? This is local minima. This is not global minima. Let's change it to some abrupt values. So one more minima is found. No, this is not minima. This is maxima. If you can see this, it is this 2 into 10 is to 40. So this can't be a minima. Let's go on this negative side. Yeah, this is also one solution. 9. Okay, so all various kinds of local minimas are found. Okay, if I plot this, let me just plot this. I want to plot this. Can I use Wolfram also? from alpha. I just want to plot this function. Okay. So I want to, no, not Wolfram alpha. There is something else. I forgot it. Paraxer used to use it, but I don't remember it right now. Um, I guess it's not there in my shortcuts. Yeah. Okay, leave it. So these are local minimas that we have find using fminunc. Okay, let's move ahead with the next problem that states that use fminsearch. Okay, instead of okay, let me first save this problem. So what was the initial condition? Minus one, one. Okay. Okay. So this is the problem one. Now what we are supposed to do? We are supposed to do with fminsearch. Fminsearch. So let do it. Fmin search. Okay. Okay, this feature use derivative free method. So the syntax is same, but the way that it is solving is different. Okay, so let's try to solve the problem. The syntax is same, correct? So let's first try to solve that same problem using fmin search. If I write here fmin search, it should give me some. Yeah, okay. So it is giving also giving same thing, 0.5 and minus 1. 0.5 and minus 1 that we are getting. If I was doing fmin unc, yeah, it was same, but function value was a bit different. That is not any making any sense because it is zero only. So let's try to solve this problem. Clear all CLC. Okay. So what is my problem statement? F is equal to at the rate of x, then 4x1 square, 4 into x of 1 square plus 3x2 square, 3 into x of 2 square plus minus sorry, minus 4 into x of 1 into x of 2 plus x of 1. Okay, this I am doing it. Now my x0 is equal to 0 comma 0, that is told to us in the problem statement, and my x comma, I can just write, yeah, x comma f well is equal to f mean search function comma x0. And if I run it, I should be really very careful with writing it. So my FL is only minus 0.0937. So minus 0.1 and minus 0.1. So my correct answer is option B, minus 0.1. Let me check it. Am I getting minus 0.1? Is it correct? Yeah, it is correct. We are getting minus 0.1, minus 0.1. So this is local minimum. If I use that fminunc, so that is also giving the same solution. Okay. Let's move ahead with the next problem. Now, here there is something interesting. Consider the function f of x with starting point x0 is equal to minus 1.2 and 0. Using MATLAB function fminsearch, find a point where the value of f of x is minimum using the optimset options to set optimization options to display all iterations and set function tolerance to 10 to minus 8. Okay, let's do one thing. Let's first solve this problem. Okay, let's first go to optimset option. Optimset set. So optimset is equal to name comma value. Okay, these options we can use. Okay, we can give various that names. Okay, so let's first try to solve that using our normal thing before using this optimset thing. Okay, let me first save this problem. Okay, control S. This is my problem 2. Okay, so now let's move ahead with the next question where we are supposed to, let's first write down the function PLC. Okay, my function f is equal to at the rate of x, then my equation is 100 into x of 2 minus x of 1 square, 1 square plus 1 minus x of 1 whole square. So 1 whole square. So this is my function. It's better to keep whole. Okay, let's say my x0 is equal to what is given here. Initial guess is given to us as 0, 0, 0, and my x, f12 is equal to fminunc. I'm using this because it is showing me that tolerance. That's why f, x0. Okay. So what is the solution that I'm getting? This 0.0365 and this into 10 raised to 11. Something really odd values that doesn't make any sense. So this problem appears unbounded. So this we can't solve it, and this options of objective limit is minus 1 into 10 is to 20. Okay, so this we can't solve. Okay, if we search, if we do it using fminsearch, I guess it will work. No, this is also not working. So what are we supposed to use? We are supposed to use some additional constraints using optimset. So how can I do it? So I have to use optimset thing. So I can write options. Okay, not here. Options is equal to, I'm writing optimset with I will be writing display thing. So it will display whatever I want to see. Then iterations, it will display iterations. Then tolerance function, and that is equal to what is told to us 1e minus 8. And here I have to use options. Okay, if I do this, yeah, it is running, right? It's not. Wait, let me put it here and let me redo it. I also need to give here exit flag. We have made some mistake in writing the functions 100 into x of 2 minus x of 1 square. Yeah, only this term is multiplied with 100. So this is our mistake. Yeah, now it's correct. Now if we run it, no, still it's not working. I am making some mistake. Okay, let me check my function again. 100 into x of 2 minus x1 square whole square. Yeah, here it should be 1 square. I have not added it. Yeah, here it is 1 square. Okay, I'm just writing is raised to 2. This is the issue. That's why we are not getting correct solution with any of the methods. Okay, so my tolerance function value is 3.682 into 10 is to minus 10. I guess this is not needed. So at each iteration, we are getting these values. Okay. Okay, so let's see if I am giving it minus 20. I don't know if it will work or not. I will just increase my iterations, nothing else. Yeah. See, so answer is always 1 comma 1. It is not exact 1 comma 1, but so this is how you can use it. Okay, I just want to see it again with that thing. Fminsearch. Instead of fminsearch, I want to use fminunc. Okay. So this is how we can solve it. So we are supposed to use fminsearch. But if I remove it, it will also okay. It will show me everything. Okay. So I'll saving it with problem 3 in assignment 11. Okay. So let's move ahead with the next problem. Okay, let me just edit this. Just give me a minute. To square. Okay. So this is how you can edit. So our correct answer is 1 comma 1 that we are getting. If I start with something else, let's say 20 comma 20, I'm not sure if we will get it or not. Yeah, it is getting 1 comma 1. Okay, so we are supposed to 0 comma 0. So let me save it with that way. Okay, so our next problem is same thing. local minima we are supposed to find. This time my equation is different. So let's do it. Same problem. Okay, I just want to see one thing. If I just remove these two things, let me keep it like this. If I remove these things, it will just keep, it will just show the tolerance. It will not show me everything. Yeah. Okay, this is something also we can do instead of showing everything. Okay. Okay. So based on our need, we can do this. Okay, let's do it. Clear all. CLC and my next function f is equal to at the rate of x. Okay, what is my function? X1 square plus x2 minus 11 whole square, x of 1 square plus x of 2 minus 11. Okay, let me just write it the way I write. Plus 11 whole square plus x2 square minus x1 plus x of 2 square, x2 square plus x1 minus 7, that 2 whole square. I just put one, it's not required. Then I need to give options. Okay, let's first give x0. What are we told to start with? We are supposed to start with minus 5, minus 5, minus 5, minus 5. Okay, and my function. Okay, first I will use options. Options is equal to optimset of, I just want these two things. I don't want to write this whole thing. So I'll just copy it. Okay, what was tolerance here? It was, I guess, minus 8. Okay, I will just copy this thing here. Okay, what is told to us? Tolerance of minus 8. Okay, then I write x comma f value is equal to what function we are supposed to, I guess it's fminsearch only. Yeah. Fminsearch of f comma x0 comma options. Okay, I'm getting it as minus 3.8 minus 3.2. So minus 3.78 minus 3.2, 3.28. My correct answer is answer A. Yeah. If I also write it here, exit flag. So what does this exit flag means? So let's search exit flag. How it will help us? Zero meaning number of iteration exceeded the maximum iterations. One meaning magnitude of gradient is smaller than the optimality tolerance. Two meaning change in x was smaller than step tolerance. Like that, there are various exit flags available, but it's not required. Okay, so let me just do one more thing. It is just for my convenience, not for you. Yeah. So, okay, we have solved this problem. So I will just save it. Okay, so till now, what did we do? We first solve our normal optimization problem or minimization problem, whatever you want to say. Then in next step, what we did, we changed the tolerance. Now, what if we are having some constraints? So for that, we'll solve the next problem. Consider the following optimization problem: 100 into x2 minus x1 square whole square plus 1 minus x1 whole square. And constraint is x1 plus x2 is less than equal to 4, 2x1 plus x2 is equal to 1, 0 to 0.4 for both x1 and x2, with an initial guess of 1 comma 1, and we are supposed to use fmincon. Okay, so let me search. Let's first search what is fmin. Find the minimum of constraints non-linear multivariable function. So see, my constraint is c of x is less than equal to 0. First is there. C equation is equal to 0 is also there. Ax less than equal to b. Ax is equal to b is not there. This thing. Okay, bounds is given. Okay, so if you follow this thing, so my format is this. Okay, so let's first write down this I have saved. Yeah. Let's write down first. Okay, here all and CLC. Okay, so now equation is same from the problem number 3. So I'm not writing it down here again. I'm just copying that equation from here. C to control V. Okay. Now, okay. So what are we having? We are having A, B, A, Q, B, Q. So we are having something CQ in our term and C of X less than 0. So these two things are there. We don't have this A and B is not there, and AEQ, BEQ is not there. So what I can do, I have to start writing the code. So I will just follow one general format. So A is not there, so I will write it as null matrix. B is also not there, I will write it as null matrix. A EQ is also not there, so I will write it as null. And B EQ is also null. Okay. Now I need to define my lower bound and upper bound. So my lower bound, what is my lower bound? My value of lower bound is, in our case, what is there? 0 is lower bound and 0.4 is upper bound. Okay, so lower bound for one is 0, another is also 0, and value of, sorry, I have written upper bound. Lower bound is 0, 0 and upper bound is 0.4, 0.4. Okay, now what is my solution? X comma f well is equal to f mean con in bracket. I will just write it from here and we will see what we have missed. Function, we have written function, then this whole thing x0 ab aq bq lb ub. Okay, function, then x0 we have not defined yet, so let's define x0. So what is the value of x0 is told to us? X0 is equal to 1 comma 1 transpose. So I will just write it 1 first row first column then 1. Okay, so I have x0, then I have ab a. Okay, it's not fun in our case, it is just f. Then a comma b comma aeq comma beq. Correct. Now further what we have? LB, UB, lower bound, upper bound, LB, comma, UB. Okay, so one more thing that we need to define is non-Lcon. NONCONONLCON. So for that, we need to write a function for that it is satisfying these two conditions. Correct? So my function, what it will give me, it will give me value of these two. C comma CEQ. Okay, so function C comma CEQ is equal to non-linear con, or you can write anything. Let's say I am just writing constraints. It's easy to understand. Constraints of, what are the constraints of X? So my first constraint C. What should I write in C? It should be less than equal to 0 kind of equation. So what is that equation? Less than equal to 0. So x1 plus 2x2 minus 4 is less than equal to 0. So x of 1 plus 2 into x of 2 minus 4. So this is my first constraint. Okay, this is not looking bad at all. This is not looking good at all. And my CQ is equal to, what is that equation? From here, CQ should be equal to 0. So we have that kind of term, right? 2x1 plus x2 minus 1. 2 into x of 1 minus x of 2 minus 1 is equal to 0. And I will end it. So I have everything. So if I run it, okay, we have made some mistake in line 18. X of 1 plus 2 into x of 2. It is issue with something else. Not enough input arguments. We have 2x, right? X of 1 and x of 2. So why is it showing? Yeah, okay, here. I need to add iterate because function is at the below. Okay, so now if I solve it, so we have, what are we supposed to say? What are we asked with an minimum function value using? Okay, here I have made a mistake. It is plus sign. Okay. So let me just do one thing. Let me remove this semicolon. So, okay. So what is asked? With an initial guess of this, solve for the minimum function value using fmincon in MATLAB up to one figure after decimal. So our answer is 0.52. Okay. So this is really easy. You just need to take care of the format of equation. You need to take care of this part. Okay. So I'll just save it. Problem 5. Oh, not there. Okay. Let me just do one thing. Here. I will open it. Okay. Now let's move ahead with problem number 10. Problem number 6. Sorry. Okay, so now my function is something different. X of 1 minus 1.5 whole square plus x of 2 minus 4 whole square. So my my c of x is less than equal to 0. I have that kind of equation present. C of x is less than equal to 0. CQ equal to 0, that is not there. Okay. And A and X are there because minus 2x1 plus x2 is less than equal to minus 1. That term is there. This is not there and this is also there. So let's solve this problem. So here, okay, I'll copy this problem statement. I just need to change the function and constraint. So first thing that I need to do is I need to write down my correct equation. So my correct equation is x1 minus 1.5 whole square. So x of 1 minus 1.5 whole square plus x2 minus 4 whole square. X of 2 minus 4 whole square. Okay. Now here my a and b can't be 0 because my a and b is here. Ax is less than equal to b. Here it's not equal to b. So ax is less than equal to b. So my a is minus 2 comma 1. Minus 2 comma 1 and my b is minus 1. Okay, now AEQ and BEQ terms. So AEQ and BEQ terms are not there here. So these two are 0. Then my lower bounds and upper bounds. Lower bound is 0 and upper bound is 4. So let's keep 0, 0 and 4, 4. What is the initial guess? Okay, initial guess as the midpoint of the bounds. Okay, midpoint of the bounds. So my initial guess x0 will be lower bound plus upper bound divide by 2, but here LB and UB are vectors, so I will use slash dot option. Okay. Okay, now this thing is remaining same. Now my constraint is, what is my constraint is 4.5 x1. That is C term, right? C is less than equal to 0. So my C is 4.5 into x of 1 plus x2 square plus x2 square minus 18 is less than equal to 0. And my CEQ is nothing. So it is blank, null matrix. Okay. So if I run this, I'm getting 2 comma 3. So what I'm supposed to say? Okay, there it's not clear, but my answer of x1 is 2, x2 is 3, and my f value is 1.25. Okay, so this is how we can solve this. Problem number 6. Okay, let's take problem number 7. We have 7, 8. Okay, we have 2 more problems. Okay, let's do this in next class because we are almost up to time. So problem number 7 onwards, we will do it in next class. So in today's class, what we have learned how we can use PDE toolbox to solve PDE with boundary conditions. We have took some examples of heat transfer. Then we used fmin, UNC, various kinds of function like fmin, UNC in the first problem. Then we also used fminsearch. Then we also learned how to use optimset to able or to set some constraints of tolerance. Then we also used fmincon function when we are dealing with constraints. So non-linear constraint they are generally saying. So this is the format that C of x is less than equal to 0. CEQ is equal to 0. ax less than equal to b, a equation into x is equal to b equation, and lx, lb and ub are lower bounds and upper bounds. So this is how we can solve minimization or optimization problems using MATLAB. So in next class, we are going to solve these problems from problem 7 onwards, where we are going to find the optimum minimum possible surface area of a cone. Then we are going to calculate the optimal radius for minimum cost of heat exchanger. And then we are going to learn, okay, these are some theoretical questions. And then we are going to learn about data fitting. So there are many problems available for data fitting. So this we will do in next class. Okay, so this is what it was for today's session. So if anyone is having any query regarding to the this course, please feel free to write me an email on this email ID. I will try to respond as quickly as possible. So that's all from my side for today's session. So thank you everyone for joining and stay safe.